Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, here we go with our next lesson. In this lesson, we are going to talk about strategies for adding integers and rational numbers together. In the last lesson, we talked about strategies for adding integers together, whole numbers and integers. And today we want to make sure we understand exactly what we're talking about when we talk about rational numbers. So I've drawn this kind of it's like a Venn diagram, but it's not the typical type of Venn diagram that you're used to seeing. There are a lot of different sets of numbers. You've got the counting numbers, you've got whole numbers, you got integers, you got rational numbers, you got irrational numbers, you got real numbers, and then you got imaginary numbers, which I'm not even going to get into that right now. Those that complex set of numbers. But the first numbers that we think of are counting numbers, right? Whenever you count anything, you always start with one. You know, if you're going to count the number of pencils in your desk, first one you pick up is number one, right? And then number two, number three, number four, and so on. So that's why we call them the counting numbers, although I think technically they're referred to as natural numbers. And then whole numbers. Somewhere along the line, maybe 2,000 years ago, it was either the Mayans or the Babylonians. I'm not quite sure exactly who came up with it, but they decided zero needed to be a part of our set of numbers. So they added zero to the counting numbers and called them the set of whole numbers. So notice in this circle for whole numbers, all the counting numbers exist in that set, but the zero is not inside the set for counting numbers. So zero is not a counting number. You don't start with zero whenever you count something. You always start with one. Zero is a whole number. And then we talked about how the integers were all of the whole numbers plus their opposites. So anything that's a counting number, anything that's a whole number is included in the set of integers. But the set of integers also includes all of their opposites. So the negative numbers, the negative counting numbers are also in there. Now we get to the set of rational numbers. The set of rational numbers consists of all integers and the decimal numbers, fractions in between them. So if we think of this number line here, 0, 1, 2, 3, those would be whole numbers that are on the positive side of this number line. And negative 2, negative 1, negative 2, negative 3, going all the way to negative infinity would be the negative numbers, which would be the negative integers. Anything that's in between, like just right there, that number right there would be 1/2. That's an example of a rational number. This number right here would be negative 1.5. That would be an example of a rational number. So rational numbers, if you think of the first ratio, a comparison of two numbers, they can be written as fractions, okay? So a rational number is any number that can be written as a fraction with an integer in the numerator and denominator. This one could be written as negative 3/2 so that it fits in with that definition. So anything that is a counting number can be written as a fraction, right? 2/1, that's a counting number, but it's also a whole number, it's also an integer, and it's also a rational number, okay? So we are going to be dealing with not only integers today, but also numbers that have fractions or decimals. Another term I want you to look at here is absolute value, because we're going to be doing some work with absolute value today. So the definition of absolute value, it's often confused with opposites, but they don't mean the same thing. The absolute value of a number is the distance that number is from zero on a number line, and it's always expressed as a positive number. So if you take this number 1/2, its absolute value is 1/2 because it's half of a unit away from zero. If you take this number here, negative 1.5, the absolute value of that number is 1.5 because it is 1.5 units away from zero. So about absolute value, we're not talking about whether something is positive or negative. It's just the number of units. If you were to measure something, how far it would be from zero. One example I like to bring up in class is a situation where it's like, if I borrow $5 from you, you are giving me the $5. So it becomes a negative because it's leaving your possession, and however much money you now have $5 less. For me, it's a positive because I'm gaining $5. Now, when we turn around and I go off and I do some work and I finally get some money and I can pay you back, and for me, giving it back to you is like a negative for me because let's say I earned $100, I have to give you 5 of that back, so now I only have 95. So it's a negative for me, but it's a positive for you. So whether a number is a positive or a negative is really a matter of perspective. And a lot of times in problem solving, we think of a negative, like if you dig a hole 5 feet deep, we might say that's -5 because it's going below the surface of the ground. 5 feet is 5 feet. There's no negative markings on your rulers or anything like that. Okay. So when we're talking about absolute value, you're just talking about the number with no regard whether you are adding it or subtracting it, whether it's a positive or negative. You're just looking at the number. Okay, so today we will continue to explore how to combine integer and rational number lengths in multiple ways to find a new length. You will also continue to learn how different combinations can be written with numerical expressions, such as this one, 3 + 3 + -2 + 11. Okay, so to get started, please copy down these 2 expressions and try and figure out what the value is. Now, if you think of it in terms of Cecil on the tightrope, remember, this is saying his first step is 8 feet, then he goes backward 3 feet, then he goes forward 2 feet. How far did he go completely? So it says assume that the number represents lengths in feet. So your answer is a number of feet. Same thing here, but now we're dealing with some rational numbers, but the concept is still the same. The first step is 12.25 feet, then the next step is 7.5 feet, and then the third one goes backwards 1.75 feet. Okay, so pause it, see if you can figure those out. Try not to use your calculator, see if you can figure it out on your own, maybe even do it mentally. Okay, let's see how you did. First thing I would think of is, remember how commutative property, how you can rearrange the order of numbers? If I add the 8 and the 2 together, that's 10, and then 10 minus 3 gives me 7 for an answer. So the answer to this, 8 + -3 + 2 is 7. Here, I might actually consider adding these 2 together first, which we would do anyway, right, going from left to right. But now you're going to take away the entire decimal part, and then one of those ones there. So instead of 19, you got 18, so it's going to be 18 feet. All right, now let's do some exploration here with the idea of Cecil on the tightrope. Let's say that his tightrope from A to B is 5 feet long. If he begins at point A, right here, write 2 expressions that will make him end at B. What do these expressions have in common? Okay? For part B, please explain why 5 + 2 + -2 is equivalent, which means the same thing, is just moving 5 feet to the right. And then part C, will 5 + 2 + -2 + 2 + -2 get Cecil directly to point B? And will this expression also? How would you describe his movements in these cases? Okay, spend some time thinking about some responses for that, put it on pause, and come back when you're ready. Okay, so for 43A, 2 different expressions, and there are an infinite number of expressions you can do here. I just chose a couple. 7 + -2 would be moving 7 feet to the right, or 7 feet forward, then 2 feet back, puts him at 5 feet. That's point B, right, because it's 5 feet. And then 2 + 3, you go 2 and then go another 3. That's also 5. So what do these have in common? They both have a sum of 5. Now, why would 5 + 2 + -2 be equivalent to just moving 5 feet to the right? Well, notice what's happening here. What is 2 + -2 equal to? That's equal to 0. So 5 + 0, we've got this identity property of addition that says whenever you add 0 to a number, it's always going to be equal to itself. So 5 + 0 is equal to 5. So he moved the same distance. Okay, so it's like 5, then 2, then back 2. So it lands on point B. So what's happening here? You notice how we get these zeros here, there's a 0, and there's a 0. And then in the same one here, here's a 0, and here's a 0. So how would you describe each one of these movements? All of them are going to eventually have him stopping at point B. Okay, but what did I write here? I can't even remember. How would you describe his movements in these cases? All right, what did I write? Did I expand on it a little bit? Oh, that's what I did. Okay, so yeah, so you can see that every one of these, we call these, yeah, let me do it in black here. We call this a 0 pair. And a lot of times it's helpful when you are adding different rational numbers and different integers together, look for the 0 pairs, because you can make those go away, and then it makes it a lot easier to solve these problems mentally. So here you've got a 0 pair here, 0 pair there, 0 pair there, and a 0 pair there. All right, so what if Cecil's tightrope was a number line like we see right here? With 0 in the middle, you got positive numbers to the right and negative numbers to the left. Please sketch this number line into your journal. And then what we're going to do is we're going to represent what -2 plus 3 would look like if we used it like Cecil does with his tightrope. Okay, so pause, give yourself I'll give you a little bit of time to, I'm not giving you anything, I'm moving on, but you're pausing and manipulating the video. Okay, so you know what to do, pause and come back when you're ready. Okay, so what would that look like if we were to start, if we were to do -2 plus 3? Well, what I always say is this is your starting point, right? So let's start at -2. And what does plus 3 mean? Does that Cecil going forward, or is he going backward? He starts at -2 and then he goes forward 3 units. And so forward on his tightrope is like moving 3 units to the right, correct? 1, 2, 3. So that is plus 3 movement, which means that -2 plus 3 must be equal to 1. So you start at -2 and you just move 3 units to the right. Your final answer is going to be +1. That's where he's going to stop there. On the same number line, start at 3 and represent these two motions. You got 3 plus 2 and then 3 plus -2. So I'll clean this up a little bit. Let's try this again. So what does it say? Start at 3. So we're going to start here at 3, and then we're going to do it one way. I guess I'll do this one in blue, where he goes 3 plus 2, 1, 2. Puts him at 5, right? So 3 plus 2 is 5. And then if we go in the other direction, because it says to go plus a -2, that means we're going to the left, 1, 2. And that puts him at 1. So 3 plus -2 is equal to 1. So what is, how are they similar and how are they different? Well, 3 plus 2 starts at 3, but it moves 2 units to the right, whereas 3 plus -2 moves 2 units to the left. So that in mind, describe how the two computations, 5 plus -5 and 8 plus -5 and 8 plus 5, how they would be related on that number line. Go ahead and formulate your thoughts and write down a quick response based on what you saw me do up here. All right, so what is your response? Both of them start at 8, correct? And both of them move 5 units. It just so happens that -5 means you're going to move 5 units to the left, and +5 means you're going to move 5 units to the right. Okay, so we are throughout 7th grade going to be adding positive and negative numbers together quite a bit. And there are going to be a few different strategies that you can use. The number line, visualizing what's happening on the number line. The first number is your starting point, and then this tells you which direction you're going to go, and the next number tells you the number of units you're going to go. I guess that's not quite right, because that you go right, but then that tells you to go to the left. So we'll talk more about that in the future. It's not my favorite tool to use, but for some students that learn with this, this is what they think about when they're adding positive and negative numbers together. And so, you know, it's a useful tool. All right, we got a lot of highlighting here. I want to make sure we read through all of this and understand each part of the direction. So in C and D of problem 44, you may have discovered that for for each of the pairs of computations, the distance that you moved on the number line from each starting value was the same. This was true even though in one case the number was positive that was being added, and the other one it was negative. The sign of the number told you the direction to go in, and the size of the number told you how many units to go, how far to go. So the amount that you moved is one way to describe absolute value, okay? And we already talked about that. Absolute value is the value of a number without regard to its sign. Now it's supposed to be sign there, sign, misspelling, or the distance it is from zero. That's what we got in our notes at the very first page, okay? So we're talking about absolute value. Doesn't matter which direction it goes, what's the actual number, that's the absolute value. So these are what we call absolute value signs. They're like, kind of like parentheses, but they're straight up and down, okay? And what you need to do is treat this like they are parentheses. You must simplify what is on the inside first, then take the absolute value of your answer. So if you think of PEMDAS, the very first priority is given to the parentheses. Technically, the parentheses are all grouping symbols. And the absolute value bars are an example of a grouping symbol, okay? So you have to simplify this first before taking the absolute value. So copy down these four expressions. Then I want you to identify, find out what the absolute value is, and you'll have to start by thinking about what we did on the previous slide, on the previous page, about here's your starting point, and you're going to go to the left 5.3 units. You started at -20 and you went 5 units to the left, you'd be at -25, right? But you're not going 5 units, you're going 5.3 units, so you go another 0.3 of a unit, and that puts you at -25.3. Well, how far away is this from zero on the number line? It's 25.3 units. So the answer to this absolute value expression is 25.3, okay? So go ahead and do the same thing for these, and then we'll check your answers. Go ahead and pause. Okay, so how'd you do? 45 plus 7.7 is 52.7, and that's 52.7 units away from zero, so the absolute value is 52.7. This is a little tricky because this says to take the opposite of the absolute value of 8 plus 81. Well, what is the absolute value of 8 plus 81? It's 89, so you have to take the opposite of the absolute value of 89, so that's -89. Okay, so having the minus sign or the negative sign on the outside of the absolute value bars makes a difference. Okay, so we'll talk more in a future lesson about the difference between opposite and absolute value, but the answer to this is -89. And then here, what do you get when you start at 0 and go 3 units to the left? You get -3. So we have to take the opposite of the absolute value of -3. What is the absolute value of -3? It's 3, so we have to take the opposite of 3, and that gives us -3 for an answer. All right, Cecil's newest act. For this act, he starts at point A on the left of his tightrope and walks on the tightrope, turns around, sometimes many times, and then ends up back at point A on the left side of the tightrope. So work with your team to write at least 3 expressions that show how Cecil could move and still start and end at point A. What are 3 different expressions where that might happen? Go ahead and pause and see if you can. Okay, so what we're going to do here, I mean, if you did 3 expressions, there are so many different ones that you can do. I didn't bother writing them down, but you could have done 3 plus, now let's say 13 plus -13. You could have taken -28 plus +28. There are tons of them. What do we notice about them? They all end up equaling 0, correct? So what all these have in common, all your expressions should have a sum of 0. Whatever you chose to write, if when you add them together, you get an answer of 0, then you've done everything correctly. You would have started at A, moved to wherever, and then moved back, because these movements are basically canceling each other out. Now, build 3 more expressions similar to the expressions you wrote up here. For your 3 expressions, one with 2 numbers, one with 3 numbers, and one with 8 numbers. Holy moly, what do all of yours have in common? All right, go ahead and pause and work through those and see what you get. Okay, let's see how you did. Basically, I mean, you're going to have an infinite number of possibilities. So the first one where you had 2 numbers, I just added opposites together, right? 3 plus -3. The one with 3 numbers, we wanted to make sure that these add up to 7, so it'll cancel out with that -7. And then here, where are our 0 pairs here? You got your 4 and your -4. You've got your 5 and your -5. You got your 2 and your -2. And finish up with the 1 and the -1. So they're going to have all a sum of 0. Okay, now let's take a look at some absolute value situations. Sally lives in North Dakota where the winter temperature is often below 0. One day the temperature was 10 degrees below 0, so that's like a -10, right? But it rapidly rose 15 degrees. So is it going up or is it going down? Is that a plus or is that a minus? Then it dropped 15 degrees as night fell. What is the resulting temperature? Draw a diagram to represent this scenario. Okay, so do you notice this whole, it rose 15 degrees and then it dropped back down 15 degrees? Where is it going to end up? Where it started, right? It should end up at 10 degrees. So how would we draw that? I put a little degree sign in there too. How would we draw that with a diagram? Well, this is how I would do that. Start with a number line that will accommodate your starting point, which is -10, and then can go 15 units to the right. That's at its peak, it must have been 5 degrees, correct? So it started at -10 degrees and then rose 15 degrees. Then it went back down 15 degrees, which means we've got this 0 pair here. So it ended up ending where it started. So this would be kind of like a Cecil sort of a diagram, although we're not using the starting point A and point B, we're using number lines, but we know the starting point was at -10, and then we went through this sequence, okay? All right, so what I would like for you to do is copy down these 3 problems. Now it says here Gina was working on these problems and she has a new idea. Look, I can use these ideas to add large integers quickly without even picking up my pencil. She wrote down each of the following expressions and calculated each answer in less than 5 seconds. Talk with your team or think about on your own how she could have done this, and then see if you can figure out what those answers are mentally. Now, 5 seconds, I believe possibly A and B in 5 seconds, but I'm not buying it for C. That's a little bit trickier. So see if you can figure it out mentally. If you make mistakes, that's okay. You can always work it out. Paper, pencil, try and figure it out, but don't use a calculator. See if you can figure it out using the strategies that we've used, okay? Go ahead and pause and work through those. Okay, let's see how you did. Now, did you notice that these cancel each other out? Which means that our answer would be 212.72. I absolutely believe Gina might have gotten that in less than 5 seconds. Here, if you take away the 300 from that, you're left with 13 6/11. So I can believe she got that in less than 5 seconds. But this one, how would we even think about that? Well, first of all, if you can recognize that 212 is what you get when you add 150.75 to 61.25, then you can picture these zeroing each other out, leaving you with 61.25. Okay, so in some situations, it does facilitate mental math, make your job a lot easier to understand how forming these 0 pairs together can make it easier to do subtraction, but it's not always that easy. So, you know, there are some times when you're just going to pull out the calculator and you're going to do it with your calculator, or if you don't have a calculator, just pull out your piece of paper and write down the problem and figure it out. All right, so this is the last question, the last problem that we're going to have for today's lesson. Consider Cecil's movements on the tightrope as you answer these questions below. We're going to use a different kind of a modeling now, and this is actually one that I prefer. I think this is brilliant. What happens when Cecil goes 5 feet and then goes back 5 feet? Where does he end up? Well, we all understand that now, right? He ends up where he started, because 5 forward is like +5, and going back 5 is like -5, so 5 minus 5 is 0. Chad decided to record Cecil's movement with this different kind of a diagram at the right. Now, do you know what those plus signs represent? Those are positive steps. 1, 2, 3, 4, 5 feet. What the minus signs represent? Those are negative steps or subtraction steps, where you're going backwards 1, 2, 3, 4, 5. Notice that each one of these, when combined, makes 0. So we call those 0 pairs. And we're going to get into that a little bit more in a future lesson, so you don't necessarily have to write all this down right now. But that's precisely what's going on here is you're getting 5 plus a -5. Every one of those combinations is a 0 pair, and so they go away, they disappear. So if I were to do something along these lines, it's like, okay, let's start with, boom, boom, hold on for a second. You've got, that's a 0, so it goes away. This is a 0, so it goes away. This is a 0, so it goes away. And there's a 0, it goes away. And there's a 0 that goes away. There's nothing left. So your answer is 0. Okay, so the 0 pairs go away. Using the same strategy, Chad recorded a different set of instructions for Cecil with the diagram here at the right. What do you think this diagram could represent? What math problem does that look like? Well, I thought it looked like probably 9 plus -3, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 plus 3 negatives. So if we thought about those 0 pairs going away, there's one 0 pair that goes away, there's a second one that goes away, there's a third one that goes away. Probably, since you can't do that, I would recommend you do this instead. Just, maybe I'll change the color here. Just circle the 0 pairs, forming a big 0, okay? So 0 plus 0 plus 0 plus 1, 2, 3, 4, 5, 6 means that 9 plus -3 must be equal to +6. Because if we take that 9 and break it apart, it becomes like 6 plus 3, and then plus the -3. So the 3 and the -3 make your 0, so you're just left with the 6, okay? So we'll get more into that later. Good job. Just make sure that you're showing all your work, and soon you'll be able to, when you're showing your work and they say draw a diagram, you'll have the luxury of choosing whether you draw these pluses and minuses to form 0 pairs, or whether you choose to use a number line like we did earlier in the lesson. All right, take care. Bye.
Hey, feeling good, like I should. When in dark,